Good morning everyone. I hope all of you are doing well. This is the high time to invest regular 1 hour, 1.5 hour time for your Olympiad examinations. IOQM. I hope all of you have applied for IOQM. In this IOQM examination, you will be preparing number theory, algebra, geometry, mainly these three topics, and you have some idea of your class 9, 10 and 11, 9 and 10 syllabus mainly, because IOQM is not so difficult. So in the past video, past live session, I have explained co-prime numbers and some related problems. We have not started solving any Olympiad problems, but the concept we will be discussing here will help you to start solving past papers, past year's IOQM papers or RMO papers. So first learn the topic properly and then go for solving Olympiad questions. IOQM also not matter of joke. You have to invest regular 1 hour minimum time apart from your school based examination or board based examination regularly. Today I have planned to do prime numbers and its distribution. I will be covering the fundamental theorem of arithmetic also and we will see related problems. But these sums are not extremely difficult. All of you be ready with a pen and paper with me and start solving the sums when required. Concept you learn, you can, that's why you are studying with me, no? You be ready with your pen and paper and start solving sums or the theory portion I explain here. Then it will work best for you. Okay? I am trying to sit every Sunday one session with you for Olympiad only. Clear? Some other videos I share with you, those are also required, like inequality video, fundamental principle of permutation combination. I hope all of you are getting ready by seeing all those videos. Without wasting time, let us start now. So this class will be doing prime numbers. Prime numbers and their distribution. Many interesting facts you will learn today regarding prime numbers. What are the facts? Let us see one by one. First we go by definition. This is a natural number greater than 1 that has no positive divisors other than 1 and itself. A prime number you cannot factorize. It has factors itself and 1. The only prime number even is 2. Other prime numbers are like this. If you try to factorize, you won't get success, these numbers. And you will observe that these prime numbers are not following any particular sequence. They are all odd except the starting one. That's true. They are all odd prime numbers. Prime numbers are odd only. And the gap between 3 and 5, 2, 5 and 7, 2, here it is 11, here again 2, here 4, here 2, here 4, here 6, like this. So they do not follow any pattern, at least for large values greater than equal to 6. That will come in Fermat's prime when you understand, when you learn. Let us go through some basic properties of prime numbers. What are those? Uniqueness. The only even prime number is 2. All other prime numbers are odd. That I have stated you already. Infinite primes. There are infinitely many prime numbers. I will give you a proof also. There are infinitely many prime numbers. There is a very interesting proof for it also. I will give you the proof. Prime gaps. The difference between consecutive prime numbers increases as numbers get larger. Here you have seen that the difference between consecutive prime numbers 2 or 4 or 6 like that. But consider a prime number, say we are taking 53. Next prime number, what is the next prime number after 53? Not 54, not 55, 56, 57, 58, 59, 60 is also not prime, 61. Okay, gap is increasing. Then if you consider prime number of 3-digit numbers, then the gap will be more. Do you understand? Gap will be more. If you go on increasing the size of the number, then the difference between two consecutive numbers goes on increasing, and they are infinite in number. Okay? Prime numbers become less frequent as numbers get larger, but they never completely disappear. This is by observation. We will observe that prime numbers gradually increasing. In the number system, it's gradually decreasing, but it will never disappear. Even you go for 24 digit, 25 digit, whatever number of digits, you will get a prime number. There is a long gap between consecutive prime numbers over there, but a prime number will exist always. It has no end. Starting with 2, it has no end. It continues. This distribution can be studied using prime number theorem, which approximates the number of p primes less than a given number n. Let us know, to understand all these things, let us make some important observations. These are actually theorems also. All these proofs can be given, but before your Olympiad examinations, I am not going for proof of every theorem here. Just why I name this one as observation 1. If p be a prime number and a greater than or equal to 1 less than p, then p is prime to a. This is quite obvious. Take a prime number, say 19. 19 is a prime number. Take any number less than 19. 12. 12 and 19, their GCD will be equal to 1. You know this symbol is used for writing GCD. 12 and 9 is their GCD is 1. Any number less than 19 you take, it is prime to 19. This is first observation, very important observation. P be a prime number and a is an integer greater than p, and p is not a divisor of a, then p is prime. Let me explain this part. P is a prime number and a is an integer greater than p. P is not divisor of a, then p is a prime. This is, suppose a number I am considering 12 and the prime number 17. This is actually stated in the previous observation only. Any number less than 17 is co-prime with 17. I mean any prime number. Understand what I say? Between 12 and 17, if we consider, then this 17, this number 12 is less than 17 and 12 is not a factor. Okay? P is a prime number, a is an integer, a is an integer greater than p, we will consider. A is an integer greater than p. That integer greater than this prime number, you take any prime number, 21, any integer greater than 21. If 17 does not divide 21, then 17 must be prime number. Okay? P be a prime number, a is an integer greater than p. P is not a divisor of a, then actually it is given for co-prime numbers. Okay? P and a are co-prime numbers and p is not divisor of a, then P must be a prime number. This is true. Okay. Observation 3. P be a prime number and A is an integer greater than P such that P is a divisor of A, then AP equal to P. For example, let us take 17 and say 102. Okay. 17 is the prime number, 102 is greater than 17. Now, if you consider the HCF of 17 and 102, the result is going to be equal to 17. Clear? P is a prime number, A is greater than P, and P is a divisor of A, then AP must be equal to P. So, as 17 is the prime number, the result will be 17 only. Next one, this is a very useful observation. P be a prime number and P divides AB, then P must divide either A or B. Okay. For example, if I tell you I am taking the prime number say 23. 23 is dividing say 69. 23 is dividing 69. 69 how can you write? 3 into 23. This 23 will divide 23 only, not 3. But number may be of this form. 7 dividing say 98. It is product of 3 prime numbers. 7 divides 7 into 7 into 2. So in this case 7 will divide one of them. So this is not only true for 2 numbers, we can take any 3 numbers also. If P divides product of 3 integers A, B, C this way, then either P will divide A, or P will divide B, or P will divide C. But the thing is that this should be expressed in the form of primes. There may be repeated primes. Suppose I am considering 7 dividing 196. Then this 196 will be what? 49 into 4, 7 square into 4 square. Clear? So you don't say that it is 7 into 7 into, not like that. It is dividing one of them, 7 or 4 over there, if it is a prime number. Clear? So this is true for product of any number of integers. But you should express that product in the form of primes. A composite number has at least one prime divisor. Suppose I am taking composite number 92. It is 23 into 4. So it has a prime divisor 23. It has a prime divisor 2 also. But suppose the number is just 21. It is 7 into 3. It has 2 prime divisors. If the number is say I am taking 9 into 7, 63. 7 into 9. So prime divisors 7 and 3 both. 9 is not prime divisor, but if you write 7 into 3 square, then we will say that 7 will divide 63, 3 also will divide 63. So composite number has at least one prime divisor always. That's why it is composite, no? Minimum one prime divisor will be there. Now this is a very important statement regarding arbitrary large gap in the sequence of prime, which I have hinted you earlier, that if you go on increasing the size of the number in the number theory, number system, then you will observe that the gaps between prime numbers goes on increasing. If you take 3-digit number, gap will be more. 4-digit number, gap will be more. Hardly will find any prime number if it is just say 16-digit number. It's very difficult to find over there, and there is no fixed rule. All those rules, sieve of Eratosthenes or that square root method which you have learned in junior classes will not work for large numbers, very large numbers. Okay? So there is arbitrary large gap in the sequence of primes. How to prove it? To prove that there are arbitrary large gaps in the sequence of prime numbers, we consider this statement here. For any positive integer k, there exist k consecutive composite numbers. Can I say that? For any positive integer k, any positive integer k, 7, we can write the existence of 7 consecutive composite numbers. How will you write this? This is very easy to write. I'll tell you. It is, say I have taken, just let us start with this example. Any positive integer k, there exist k composite numbers. I am taking the simplest one, 7. Okay? Then I am writing factorial 7 plus 2, factorial 7 plus 3, factorial 7 plus 4, factorial 7 plus 5, factorial 7 plus 6, how many? 3, factorial 7 plus 7, factorial 7 plus 8. Okay? They are all consecutive composite numbers. Why? How do you say they are composite numbers? You know the meaning of factorial n? Factorial n stands for what? N minus 1, n minus 2, four into 3 into 2 into 1. Am I correct? This is the meaning of factorial n. Now, this plus 2, it has fixed value. Suppose it is fixed value 500. 500 plus 2 is a composite number. 500 plus 3 is a composite number and consecutive. 502, 503, 504, 505, 506, 507, 508. Factorial 4 when you consider, that is 24. 24 plus 2, 24 plus 3, this is factorial 4 plus 2, factorial 4 plus 3, they are all composite numbers. You make one simple observation. Factorial 7 is a factor 2, no? With that, if we add these two, 2 can be taken common. Then remaining thing inside bracket is a prime number or composite number. It is expressed as product of 2. For this one, factorial 7 plus 3. Factorial 7 contains 3. You take 3 common from these two. Then inside bracket 7, 6, 5, 4, 2, 1 plus 1. That is a number. Maybe composite or prime, but outside there is 3. You understand what I say? Just I show you this example. I am writing, say, factorial 7 plus 6. This is 7, 6, 5, 4, 3, 2, 1 plus 6. If you take 6 common, what do you observe inside bracket? 7, 5, 4, 3, 2, 1 plus 1. This one is a number, either prime or composite. Outside there is 6. So, this is a composite number. This I wanted to tell you. And this is true for any factorial symbol you take. Like I am taking, say, factorial n. I start from there only, factorial n. factorial n plus 1, factorial n plus 2, factorial n plus 3, they are all composite numbers, isn't it? You take the number, any number n which is larger than 2, this will happen. This is going to be larger than 3, sorry, it will be a composite number. Okay? So, where is the proof that arbitrary large gap in the sequence of prime number? So, first we have seen that these numbers are composite. You start from factorial 7 plus 1, factorial 7, they are all composite number. Even you start from factorial 7, composite. But I am starting it from here 2. Then no restriction is required that n must be greater than 2 or 3. Starting from beginning only, just start from n equal to 2, it is going to be composite. No, here also you have to start with 3, where n is a large number greater than or equal to k plus 1. This you have to remember. If you have taken, if you are saying there exist k composite numbers, then n must be greater than or equal to k plus 1. Otherwise, it is not. This way you have to consider. When you are considering, that's why I have started from here, no? Factorial 7 plus 2, factorial 7 plus 3, factorial 7 plus 4. This may not be composite because factorial n, if it is 2 only, then 2 plus 1 is not composite. And factorial 2 plus 3 is not composite. So, if you consider k consecutive, then you take the number greater than or equal to, then you take the number greater than or equal to k plus 1. Then it will be useful. Clear? Let us go for checking that only. So, we are starting from factorial n plus 2. Now, it is true for any prime numbers. It is true for any prime numbers. N is greater than or equal to k plus 1, you start from 3, then it will be true. You have to start from 3 here, greater than or equal to k plus 1, 3 consecutive. So, let us do it for n. Factorial n plus 2 is a composite number because n is greater than or equal to 2. Am I correct? N is greater than or equal to 2, no, 2 plus 1. So, you start from 3 always. Factorial 3 plus 2 is a composite number. Factorial 3 plus 3 is a composite number. Composite, all are composite number. Now, this thing is divisible by 2. Am I correct? This thing is divisible by 2. What about this? This is also divisible by 2. No, this is actually divisible by 3 also. Why? Because it is larger than or equal to 3. Factorial 3 is what? If you take n equal to 3, factorial 3 is 6. 6 plus 3, 9, it is composite number. Okay? So, this thing divisible by factorial 3. Factorial n plus 4. This will be divisible by 4. Why? Because factorial n contains that 4. So, 4 you take common, then it will be composite. Factorial n plus 4 divisible by 4 and so on. These are all composite numbers. So, where is the rule? If you have taken 5, then you are saying that factorial 5 plus 2 factorial 5, they are all composite numbers. Then where is the prime number? If you have taken 7, then you have said factorial 7 plus 2, factorial 7 plus 3, all are composite. So, gap is increasing over there. You understand what I say? If we take n is equal to 3, n is equal to 3, and then I am saying that, say we are considering 5 consecutive composite numbers, then 5 consecutive composite numbers are what? Factorial n plus 2, factorial n plus 3, 4, 5, 6. If we say that 7 composite numbers, then what do you get? factorial n plus 2, factorial n plus 3, factorial n plus 4. This way it continues 7 terms till factorial n plus 8. So that is increased. You are getting 8 consecutive integers. Initially there was 5 consecutive integers, now it is 8 consecutive integers. So this goes on increasing. Next, if you take more, suppose you are taking k equal to 9, then the 9 consecutive integers. 9 consecutive integers, they are all composite. Similarly for 10, 11, 12, it goes on increasing. You will not get any pattern, which we have established here by considering this thing as any changing. So gap between two prime numbers is not fixed. You said that there will be 7 consecutive composite numbers. Then for next one, 10 consecutive composite. So gap is not fixed. So this is very important. Please keep in your mind. If you don't understand, write in the comment box. I'll help you by sharing another short video with you. Okay? So this is established fact now. Arbitrary large gaps in the sequence of prime numbers. Always there. Number goes on increasing. This gap also goes on increasing. Now let us do some problems based on the concept of this prime number and composite number. You have to prove that for all n greater than 1, n to the power 4 plus 4 is composite. How to prove this? We are doing algebraic number theory, not with the numbers, fixed numbers always, or constant like 3, 4, 5, 7 always. We are doing it for all n greater than 1, this is composite. N to the power 4 plus 4. This is another important fact. N to the power 4 plus 4, to prove it composite. Composite means it is product of at least 2 prime numbers. Can you prove that it is the product of 2 prime numbers or more than that, or 2 composite numbers? Then also it is composite. How to? I am just using simple algebraic concept. This I am writing n square whole square plus 2 square, going by method of completing square. 2n square into 2 n square plus 2 whole square. But this 4n square was not there, so we must subtract. Clear? You understand? Just going by method of completing square. It is n square plus 2 whole square, 2n whole square. N square plus 2 plus 2n n square plus 2 minus 2n. Take any number n greater than 1, any number n greater than 1, 4, 5, 6, whatever. This will be an integer, this is also an integer, isn't it? So it is product of 2 integers. This will ensure that n4 plus 4 is composite number. Am I right? You all understand? Now how to prove that n cube minus 1 is also composite? This sum is yours. You all can do it easily. For the second part, you write n cube minus 1 as product of these 2 prime numbers, n square plus n plus 1. N minus 1 into n square plus n plus 1. So this is a composite number. Product of 2 composite numbers, n minus 1, n square plus n plus 1. So it must be composite. Now this is very interesting. If n is composite, then how do you show that 2 to the power n minus 1 is composite? Will it be composite number? 2 to the power n minus 1. It will be composite. Just I want to show you the rule of expansion of terms like this, x to the power n minus, I have discussed with you earlier also. This is actually product of x minus y, x to the power n minus 1 y, n minus 2 y square, n minus 3 y cube plus y to the power n minus 1, product of these two things. Why I have written so? Because this will help us to prove this one is composite. How to prove it? N composite given. So I can write that let n equal to p into q. P into q. P may be prime or composite. It doesn't matter. Just it is given composite number. So I can write n as product of two integers. P and q are integers. Don't consider their primes. Okay, better you change the symbol. Let n equal to, as it is composite, n1 into n2. n1 n2 may be prime also. May be composite, it doesn't matter. But n is composite when I am writing product of these two. So given number is what? 2 to the power n minus 1, 2 to the power n1 n2 minus 1. This is nothing but 2 to the power n1 to the power n2 minus 1. You all agree? Now you compare with this. Why do you need to compare? Because we are getting this form only here. You can write 1 to the power n2, no problem. But 1 to the power anything is 1 only. So I am replacing y to the power n permanently, or y by 1. So by using this factorization, we can write it as 2 to the power n1 minus 1. This 2 to the power n1, 2 to the power n1 or n2, x to the power n, no, x minus y. So 2 to the power n1, n2 minus 1. You understand why? Because x to the power n minus 1. What we have taken x here? X is 2 to the power n1 and y is 1. So 2 to the power n1 into n2 minus 1. This plus 2 to the power n1 minus 2 into n2 minus 2. It continues this manner, plus 1. So for any value of n1, this is a number, maybe prime or composite. This one is also number. So this is an integer, maybe prime or not, and second bracket is also an integer, maybe prime or not, we don't care. So this thing going to be product of two integers. It means 2 to the power n minus 1 is composite. This will ensure that 2 to the power n minus 1 is composite. Am I clear? Hope you have understood. Let us go for next one. P greater than equal to Q and wait a minute, let me remove this, otherwise you won't understand. Yeah, P greater than equal to Q greater than equal to 5, P, Q are both primes. Prove that 24 divides P square minus Q square. Note this thing, P and Q, they are greater than equal to 5 and P, Q are both prime numbers. I haven't told you what kind of numbers are prime number, but I told you this must be an odd number. Only prime number exists in the world of number theory is P equal to 2. Prime number is p equal to 2, the only prime number. P is equal to 2. This is the only prime number. And prime numbers, you know, can be taken as 2q and 2q plus any integer can be taken 2q and 2q plus 1. For q equal to 1 we are getting 2, but they have said pq greater than equal to 5. So it must be of the form 2q plus 1, starting with q equal to 2, not 1, never 1. So let us see divisibility by 2q, by taking p and q of this form. So let us take, let p equal to 2n plus 1 and n1 plus 1 you write, no problem, 2n2 plus 1. Maybe n1 equal to n2. But they must be of the form 2n1 plus 1 and 2n2 plus 1. Then 24 divides p square minus q square. To prove this, I am first considering they are unequal. Let p equal to q. Then both n1 and n2 will have the value n, say. So p square minus q square is what? 2n plus 1 whole square. You write p square minus q square. No need to write actually. P square minus q square will be 0 here, isn't it? Because they are equal. P and q, this is 2n plus 1. Q is also 2n. If you subtract it will be 0. So this implies that 24 divides p square minus q square. But this is a particular case. This is case 1. Case 2, let p is equal to 2n plus 1, 2n1 plus 1, and this is 2n2 plus 1, n1 not equal to n2. You assume that n1 not equal to n2. Now, p square minus q square is what? P plus q, p minus q. P plus q, if you add these two, will be what? Twice n1 plus n2 plus 2. What do you observe? Okay, you observe later. P square minus q square, I am writing this form. And p minus q will be what? 2 into n1 minus n2. You understand? So what do you observe in this case? When p, q are unequal, see, you are getting 2h common. From here, 2h common from here also. 4 n1 plus n2 plus 1 into n1 minus n2. No idea about n1, n2. But it ensures that 4 divides p square minus q square. Am I correct? It is proved that 4 divides p square minus q square, assuming they are unequal. Now, another part is left, because 24, out of 24 I got 4 only, 6 is left. How to prove that 6 also divide p square minus q square? This time I go divisibility by 3. Let's see what happens. You will take good decision if you take PQ larger. But I am showing you step by step. After this, you apply any method. You don't have to follow the way I am telling you here. You take this manner. Let P is equal to 3n plus 1. As prime numbers are odd also, 3n plus 1, not always odd, but can be of this form. 3n plus 1, 3n 2 plus 1. you can take one of them as, say, 3n plus 1, and q you take 3n minus 1. Clear? We can take this way, because divisibility, if you consider, they are of the form 3n plus 1, 3n minus 1. Definitely 3n plus 1, 3n minus 1 will be odd for prime numbers. We are taking their prime numbers. No, that's why they will be odd. Definitely. You will say that no, if I take n equal to 5, don't. Because I said p and q are both prime numbers. So you have to think that 3n plus 1 is odd, 3n minus 1 is also odd. Clear? Now, you go by this factorization again. P square minus q square is what? P plus q, p minus q. This is sum of these two, 6n, and difference of these two, 2. See what you are getting? 12 into n. So 12 divides p square minus q square. Done. You wanted only 6, but you got one thing extra, 12. You might say that, as you told, any prime numbers you take 3n1 plus 1, 3n2 plus minus 1. You can, no problem. Same thing will arise over there. Okay? So 12 divides p square minus q square. This one is proved. And here you have proved 4 divides p square minus q square. So does it ensure that 24 divides p square minus q square? Can I say that? Because you needed another one, no? If 4 divides p square minus q square, 12 also divide p square minus q square, you have got 12 divide p square minus q square, because 4 is a factor of 12. You need another one. So it is better to consider divisibility by 4n, divisibility by 4. There will be 4n minus 4n plus 2, 4n plus 1, and 4n minus 1. Out of these 4n plus 1 and 4n minus 1, they are odd. Not always. I mean, odd definitely, but they are not always prime. But we will assume that they are prime numbers. Okay? So, does it ensure that p square minus q square now divisible by that? You better change it a bit. You take this one as, instead of taking 4n minus 1, you take 4n plus 3. That is also 4n plus 3. Clear? So, you take numbers in the form 4n plus 1 and 4n plus 3. These are two, like the previous case. So, what about p square minus q square here? It is p plus q into p minus q. This is coming what? P plus q is what? 8n plus 4, and this is what? 4n, this is 2. So you are getting 8 into that 2n plus 1. So you got a factor 8 also by considering divisibility by 4n, divisibility by 4. Here you got 12 is a factor. It means 3 is a factor of p square minus q square. And here you got 8 is a factor of p square minus q square. If 3 divides p square minus q square, 8 divides p square minus q square, this ensures that 3 into 8 divides, so 24 will divide p square minus q square. Correct? You understand? Go for next one. if 2 equal to P1, P2, Pn, where Pi are prime number, show that this can never be a perfect square. How will you prove this? What is the easiest way to prove this? This is another very good sum on prime number. If 2 equal to P1, P2, Pn, where Pi are prime numbers, so that this can never be a perfect square. You just read the sum and try to solve before I do it here. This one you try to prove by contradiction. Let us assume that P1, P2, Pn, this plus 1 equal to square of this integer. A is an integer. We are assuming that let P1, P2, Pn is equal to a square. We have assumed let it be a perfect square. Clear? So this implies what? This implies what? That P1 plus P1, P2, Pn is going to be a square minus 1. Isn't it? You have assumed that, or you take this one as the number. Now go by doing this. Let P1, P2, Pn, this plus 1 is equal to A. No, this 1 you leave. Let this be is equal to A. Then P1, P2, Pn plus 1 will be A plus 1. A is what? Product of prime numbers. And you are going to prove that A plus 1 is not a perfect square number. So contradictory statement you take this manner. Let for contradiction P1, P2, Pn plus 1, A plus 1 is equal to perfect square, B square. B is an integer. A, B both are integer. Positive integers, of course. Positive integers. A and B both are positive integers. So A equal to what? B square minus 1. B square minus 1 is what? B plus 1, B minus 1. Am I correct? A equal to B plus 1 and B minus 1. Now A you have considered what? A you have considered product of prime numbers. Now A can be even or A can be odd. For A equal to 2k, what do you get? For A equal to 2k, the 2 is the only prime number here, you know. P1 be that P1 be 2 only. That you can take. Then k is odd number. But what you get here? A you are getting B plus 1, B minus 1. This B plus 1, B minus 1, this k is odd, no, you have understood. K is odd. Now A you have written B plus 1, B minus 1. This B plus 1, B minus 1 will be B plus 1 into B minus 1 is divisible by 4. Here you have said that this is an even number, just 2 into that form. No 4 exists over there, because when you take A in this, but 2 is the only even prime number. Even if 2 included, then A must be of this form 2k, where k is odd. But here you prove that b plus 1, b minus 1 is divisible by 4. This may not be in general, but if you take b equal to 2k plus 1, you are taking b equal to 2k plus 1. Say, this one 2k, no? So b square is 2k, b square is odd. So b also must be odd. B cannot be even. So let b equal to, okay, k is already used. So from here you see, check as a plus 1 equal to b square and a is 2k, 2k plus 1 b square. This implies b square is odd. This implies b is also odd. Isn't it? See, b is odd, b is of this form 2m plus 1 or 2m minus 1. Whatever you take, this is going to be 2m into 2m, 2m, this if you take 2m plus 1, 2m plus 1 form, anyone you can take, no need to do both, 2m plus 2 into 2m. So you are getting 4 into m plus 1 into m. Check once. It's a very good sum. If 2 equal to this, where pi are prime numbers, so that p1, p2, pn can never be a perfect square. We have proved that it is coming to be 4 into that, where we have assumed that the contradiction first, let it be a perfect square. From there we are proving it is not possible. Okay. For next one, prove that there are infinitely many positive integers such that 2a is, this we need fundamental theorem of arithmetic. We are proving it first, then we will do. Now how to do this one? Prove that there are infinitely many prime numbers. How to prove it? How to prove there are infinitely many prime numbers. Similar question, prove that there are infinitely many prime numbers of the form 6n minus 1. And last one, to prove that sum of n natural numbers cannot be, all about prime numbers. Next session I will be discussing fundamental theorem. Let us complete this first. Prove that there are infinitely many prime numbers. This is actually initially I told you, go on increasing the numbers, size of the number, the prime numbers gap goes on increasing. But you cannot say that if we reach a number like 5 to the power 5 crore, then there may be, that may be the last prime number. No, it's not like that. It cannot be. It has no end, and very logical proof is there. Suppose n be arbitrary integer, n be any arbitrary integer, that n I am taking p1 is a prime number, n I am taking in this form p1, p2, pn, where p1, p2, pn are all prime numbers. Can be done. Any composite number can be expressed as product of prime. Okay. So again we consider the contradiction first. Let number of primes be finite. We are assuming that. Now let n equal to p1, p2, pn plus 1. I am taking another number p1, p2, pn plus 1. You said that pn is the last prime number, n is very large, it is the last prime number. But I am going to prove that their product, even their product plus 1 is also prime number. Why? Because this product is divisible by P1, P2, Pn, or product of any 2, product of any 3, like that. All these prime numbers up to n, they will divide this product P1, P2 up to Pn. But none of them, even you start with P1 equal to 2 even, none of them divides 1. Am I correct? Those prime numbers will be of this form 2, 3, 5. We have taken many Pn till Pn. This product divisible by 2, 3, 5. These prime numbers are their product. But when you consider this plus 1, none of them divide 1. So they are dividing this product, not dividing this product. You cannot take a common factor between them. So this one is a new prime. This one is a new prime. This implies what? This implies that number of primes, you have ended till Pn now. But here I got a new prime, huge, much larger than that. This implies that number of primes infinite. You cannot say that it will be up to this many crores or this many crores to this many crores. Not like that. Indefinite. Goes on increasing. Gap also goes on increasing. You will try this sum on your own at home. Let us do this one. How to prove that sum of first n natural number. See, today's class is introduction to prime numbers and their distribution. But I am telling you, the facts I have explained, facts I have discussed with you, very important. Number of primes infinite, large gaps are there, number goes on increasing, with composite number how to deal with, all these are very important. This is another one. Sum of first n natural number cannot be primes. Very easy to prove. This you are supposed to do, but I don't have time to wait. So let me answer this one. You start this manner. Let n equal to first n natural number. No, sum of natural number. Let Sn equal to this sum. 1, 2, 3 up to n. This sum is nothing but n into n plus 1 by 2. Okay. Number greater than 2. Numbers can be of this form. Let n equal to 2k or 2k plus 1. You can take one only at a time. For n equal to 2k, this is going to be what? Sn equal to 2k into 2k plus 1 by 2. K into 2k plus 1. It is composite. This one is a composite number, you agree? This one is a composite number. Am I correct? So for n equal to even number, the sum of n natural number is composite. For n equal to 2k plus 1, what do you observe? 2k plus 1, 2k plus 1 plus 1 by 2. 2k plus 1 into 2 you take common, k plus 1. So what is this? This one was composite and this is also composite. So taking the numbers, whatever form you like, this is going to be composite only. So it's a composite number. This can never be prime. Okay? I hope you have understood till this. Practice simple problems. I told you I am making a platform where I can share all the documents, including this live session. You wait for that. Okay? See you again. For the next session, it is going to be on Fundamental Theorem of Arithmetic. Okay?